So what I'm going to talk to you about today are the changes to the concrete provision of ASCE 41 and the new relationship that's been created between ACI 369 and ASCE 41. Let's see how it goes. So the outline of what I'm going to talk about. So there's a new ACI 369 standard that we're developing. I'll talk to you briefly about what that entails, and then looking at the concrete changes in the upcoming cycle. So we're expecting to publish 4117, and the standard 36917 will be a source document for it. The big changes, I'm going to touch a couple of very big changes, and then there's some smaller ones. Stiffness provisions for walls are being changed. The concrete column, as you get out of this seminar series, the columns are important, so we're really trying to get them as best as we can. For those of you that have used ASCE 41, the concrete provisions, we're trying to clarify what material properties to use. Currently, it's not clear whether to use lower bound, upper bound, or in the provisions, and also talk about the long-term changes. So, start a little bit about where we're at. As some of you may know, the ASCE 4113 brought together the 4113, so the ASCE 31 and the 4106. Now they're one document. This is a very sizable document. It's about 1,000 pages long. It has all the materials in it. It has concrete, steel, masonry, tier 1, tier 2, tier 3 evaluation procedures. So it's a very comprehensive and very large document. Where the ASCE 4106, the previous version, came from it was a FEMA 356 document, which was before FEMA 274. And so it went through FEMA 274, 356, ASCE 4106 with very little changes to it. So it was becoming a little bit dated at that point. So there was a supplement 1 that amended that, came in after 4106, in which the stiffness provisions of columns, beams, and joints were changed. Column modeling parameters were updated also. They were very conservative. This supplement made them less conservative, but they were still conservative. The supplement 1 also updated some splice provisions, introduced a stress capacity estimate, which was very convenient, especially if you had your splice away from the point of maximum moment. Some wall modeling parameters and strength relations were changed, and some slab column connection modeling parameters and strength values were changed. So these came in after 4106 and now have been incorporated into 4113. But now the question is how to update these and keep that document going. So the ASCE 41 committee is about 30 people strong, something in that order. They have a 1,000 page document to maintain and upgrade. Contains all the materials, concrete, steel, masonry. It is becoming a very daunting task for the committee to keep this going. And so there was a proposal to come in when I became chair of ACI 369, which is Seismic Repair and Rehabilitation Committee in ACI, to say, well, why don't we work together and see if ACI 369 can help with the provisions. And so the agreement we came to, and that was negotiated about a couple of years ago, was to take the concrete provisions out of ASCE 41. This is chapter 10, and create out of it a new standard, the ACI 369 standard. There'll be a new standard in ACI. I just took the cover of ACI 318 and changed the text on it. This is what I expected to look like for the 2017. But to get this all done, we had to work out a relationship between ACI and ASCE. So they had to come to an agreement. These would be two standards. So you have the ACI 369 standard and the ACI 41. And we don't really want them to diverge from each other. So they need to work together. You can't start doing whatever we want in ACI 369. Then it will not work with ACI 41 and vice versa. If they change all their framework, then whatever happens at 369 does not work out. So we had to work out an agreement. It was a happy one at that. And this is what the Memorandum of Understanding between ACI and SCI looks like. It was signed in early 2014. What it says is that basically all concrete proposals, so anything to deal with concrete for ASCE 41 will be brought to ACI 369. So ACI 369 is now handling all the concrete provisions. any proposal that comes through will get balloted and dealt with in ACI 369. Once we're done with it there, it goes through the ACI Technical Activities Committee review. Within that review, there's internal, external reviewers, and there's ASCE 41 would also review it at that point. We go through this, and whether before public comment or after public comment, we resolve all these comments. There's maybe some back and forth here. ASCE 41 is always on board. I am actually leading the task group on concrete in ASCE 41, so there is a communication channel there. Once all these are resolved, ACI 369 will publish a standard, and ASCE 41 will affirm it and will republish it, reprint it in its version. So as part of the negotiation with ASCE, they will reprint the ACI 369 standard, but the ACI 369 standard will become the source document for the concrete provisions of ASCE 41. What that does is, I like the system for one big reason, is the provisions get a lot of eyes on them. So 369, where the expertise in concrete lays, will go through it once. ASCE 41 will look at it also. The Technical Activities Committee will also look at it. So this can only benefit the document. The downside is this takes time. So we have to go through all these hoops and cycles, and I'll see where that plays out now. Our first cycle is very, very short. And before I go any further, I'd like to acknowledge the people that were in the room with me when we negotiated this MOU. Robert Pekelnicki, who's the current chair of ASCE 41, Peter Summers, who's vice chair of ASCE 41, myself, and Ken Elwood, who was the previous chair of ACI 369 and kind of started this relationship with ASCE 41. So what is our code cycle looking at? ASCE 41 has decided to go for a 2017 cycle, so kind of to match up with ASCE 7 and other standards and codes, which pushes us also to publish ours in 2017. What that means is that all technical changes must be completed by summer, and since the MOU was signed in early 2014, that gives us very little time in code cycle time to get things going. And what you should be expecting is we were going to go, at least for this first cycle, to joint public comment ASCE 41, ACI 369 at that point. So they will finish their balloting and their provisions, will finish ours, and we'll go to joint public comment at the same time. We'll take the comments together and incorporate them. So this is where it's going. This kind of relationship seems to be working well. I'll let you know in 2017. If all goes well, it is being also taken up by AISC for steel. So this AISC is now looking seriously into using such a system, and also the masonry people, masonry folk are actually looking at putting this in. I think this is beneficial to everybody. The material specifications and material issues are best dealt with in the material institutes, where more of the expertise is. As long as we can coordinate properly with ASCE 41. We just don't want things to start drifting off, and then we'll just have separate things that don't really work well together. So this is a quick overview. This is relatively new. And now what I'm going to talk to you about is what are the changes for the next code cycle in ACI 369. So we took the concrete provisions, and now we started the standard, and we're looking at a few changes. Because we have such a short cycle, we can only put in a few changes, but I'll talk to you also about future changes that are coming around. So one big change that we're trying to put in there is looking at changing stiffness provisions, and especially for shear walls. A quick overview of what those stiffness provisions look like. Currently in ASCE 41, you have an effective flange width equation for beams. You have an effective joint stiffness, so whether all rigid or all flexible or a combination of both. That came in through that supplement 1. And then, for the most part, what you have are these alpha factors, I'm calling them, so modifiers on the gross moment of inertia of a section. This is a table straight from ASCE 41. So for beams, you take 30% of EI gross. For columns, between 0.7 and 0.3. This was changed in supplement 1 and improved. I gross, and for walls you have this nice number that is 0.5 EI gross. And so how well are these stiffness provisions working out? I'll I had the opportunity of working on this experimental program with at E-Defense in Japan. This is a full-scale structure. This is a 4-story building. Actually, there's 2 4-story buildings there. There's one here and there's one next to it. This one here is a post-tension structure. This one here is a conventional reinforced concrete structure. It had shear walls in one direction, moment frames in the other direction, and it was shaken almost to collapse at different levels of ground shaking. Everybody likes a video, so here's one of the I took this video, so my hand is not that steady, and you'll see the ground motion start, and this is one of the higher level ground motions. There it goes. And well, the Japanese were interested in looking at the difference between conventional and post-tensioned, and I was interested in the behavior of this particular building, looking at it. So we started with the basics, starting looking at the stiffness. How does that building fare? These are the ground motions. So it was JMA Kobe 10%, 25%, 50%, 100%, followed by the Takatori motion 40 and 60%. These were imposed on the structure. This is basic detailing in the structure. I don't want you to get into it too much or read too much into it. I just want to highlight the dimensions. Columns were 500 by 500 millimeters, so we're talking about 20 inches by 20 inches. Walls were 2,500 millimeters by 250, so 100 inches by 10 inches. So sizable walls. These are fairly full-scale sections. They were this building was designed according to modern Japanese seismic design codes and satisfied most of the ASCE 318 codes for special moment frames and walls. The walls even exceeded the requirements in ASCE 318 for confinement and such. So it's essentially a seismically detailed frame. And this is the drift, the story and the drift ratios of the stories for the different ground motions. This is in the frame direction, and this is for the wall direction. So you see that distribution of story drifts. And what you'll see here is at the 25% Kobe motion, the deformations were very low. By the time you got to 50% Kobe motion, you just cleared the yielding point in the frame direction, and the wall direction at 50% also cleared the yield point not by a lot. So what I'm going to focus on here is the 25 and 50% Kobe motions. These are the ones that got us to yield and a little bit beyond yield to look at the stiffness. And the way we looked at the stiffness was we drew the secant stiffness from 0 to the peak at each of the cycles. So the ground motion would shake the building, and at each of these cycles we would take that secant stiffness and see how it changed with time with the amplitude of the motion. And this is what it looks like. So this figure, if I was to explain it here, is the frame direction and the wall direction. This is the 25% Kobe motion taken where the heaviest shaking happened, so right about 15 seconds here. And this is back to back with the 50% Kobe motion right there. And this is the stiffness of the story. So the first story, second story, third story, and fourth story. If you look at the stiffness of the frame direction, starts off here before any real ground motion was imparted, and during the big cycles the stiffness drops and levels off all the way through to the end of the ground motion, and then when the 50% Kobe motion kicks in, the stiffness drops again and levels off here. And there is a big difference from here to here, and we just got to yield somewhere around here. So this is a big stiffness change just due to cracking, not even yielding of the building or any real damage. And we see the same thing in the wall direction. You have a drop here and another drop there and the subsequent ground motion. So that was a big eye-opener. I mean, we expected to have some drop. I mean, things soften as you crack, but this is a substantial drop that we've seen. And so we looked at it and saw, well, let's see how different code provisions are doing. And we looked at ACI 318, ASCE 4113, AIJ, the Canadian code, the New Zealand code, Euro codes 2 and 8, and FIB 2010 to see how the codes are performing, we had to build a model. We couldn't just do one element by element. We had to do story by story. That's how we can compare things. So we built this model, and we build it according to each of the codes. So we use those alpha factors or effective flange widths, all the things that are in the code that give you the stiffness of the structure. We use that in the models, and we looked at the stiffness that we get out of it. And this is the money slide here. This is what we got, and it was rather surprising to us. So if we take the first story here, frame direction, and first story wall direction on the right, you look at how the stiffness changes. This is what I showed you previously, but plotted versus drift ratio. So if that secant stiffness, if it reached a certain drift ratio, this is the stiffness, then it degraded here at another cycle, then here the next cycle, here the next cycle, and then leveled off here no matter what the ground motion was at the point. So the stiffness degrades and is never recovered. Once you have a certain level of cracking that occurs, it is never recovered. What we see here, what are the big conclusions? Where is ACI 318? It's way up here in the frame direction. We're not talking 20% or 30% difference. We're talking 2, 3, 4 times stiffer. This is the stiffness you're targeting, somewhere near yield, which is down here. So if you're targeting that secant to yield, you're down here somewhere. This is where ACI 318 is. Now, after the supplement 1, column stiffnesses were changed, and so this is where ASCE 41 is. It sits much better now than ACI 318, but still maybe about 2.5 times stiffer for this particular structure. And the wall direction, we have similar and even worse condition. This is first yield here, so you're targeting a stiffness level that's about here somewhere. ACI 318, ASCE 41, this is that 0.5 EI gross is putting us way up here. Also about maybe 3 times stiffer than where this wall should be. These are big differences. None of the codes really captured the stiffness properly down here, with some doing better than others. And all of the codes were quite a bit stiffer than what that structure saw. So this was a big eye-opener, and that's kind of what triggered the change proposal in ASCE 41, and especially for the walls. And since this is doing a little bit better, it was changed to supplement 1, we didn't have much time to bring this up to par also on this code cycle, so we focused on the walls for now that are way off. And this is the wall first story, and this is the wall second story. We look at ASCE 41 here in the first story, in the second story, still quite a bit. The first story rotation really governs a lot what happens in the higher stories. So if you get the first story right, or where that big rotation is, then things get better. But what came out of all this was that FIB was here and right there. Why was FIB doing so well? And that's really started us thinking, where do we go from here, and how can we improve what we have in ASCE 41? And the way I looked at it, well, FIB is based on a moment curvature approach. And it also introduces the effect of bar slip at the interface explicitly. So what FIB does is gives you an EI effective as a function of that rotation, which is part of the wall rotation is just due to curvature. So if you take your moment curvature relationship, you look at your curvature at yield, which is here, that gives you that slope just straight from moment curvature. And this component here is the rotation that comes from bar slip at the base of the wall. If you look at what happens in the bar that's anchored in the foundation here, base of the wall or a column, you have a tension force on it. There's a stress in the bar. That stress and strain die out over a certain distance. And so if you assume a constant bond force between the bar and the concrete, what you get is this constant bond force, the stress degrading linearly over distance, and the strain degrading linear over stiffness, which we call here the strain penetration depth. And if you integrate the strain over the strain penetration depth, that gives you a certain slip up here. And if you take a rotation at the neutral axis here, you get this rotation that comes out of bar slip. So what the FIB is doing is taking basic moment curvature, which is what you get from your fiber section analysis. If you did a fiber section and you run it through, that's what you get with this first component here. and added to it that bar slip component, lumped it up to EERI effective, which seems to be working really, really well. So the advantage of this method is it's applicable to various wall shapes. So you can use this moment curvature approach to seawalls, T-shaped walls, all sorts of walls. It does account for the amount of reinforcement and the axial load. So as you're adding axial load, your moment curvature response will change. And what I find to be the most important thing here, it is consistent with fiber section methods. So currently, if an engineer goes and does an assessment of a building shear wall with 0.5 EI gross and goes along, gets their numbers and does everything with it, or you go and say, well, I'm going to use fiber section, which is not that uncommon now for shear walls, you will get what the FIB is giving you or something close to it. You could be off by a factor of 3, whether you go one way or another. And what this kind of methodology will do is actually will bring these two in alignment. And so here's what we're proposing. This is currently under ballot. The ballot closes on Wednesday. And next week in ACI, we had positive feedback at the summer meeting, so I'm thinking this will make it through. What we're proposing here is to go straight off and say, well, your EI effective is the moment over curvature at yield. So this is just the slope of your moment curvature, diagram, and separate the flexural behavior from the bar slip behavior. So this is just pure flexure straight off from your moment curvature analysis. And then add a rotational spring here that has this stiffness, which comes from that bar slip. And that stiffness was evaluated using a constant bond stress of 12 root F prime C in PSI units, which came from a very large column database. We found that that number works out really well. And this number gives us a strain penetration depth that's here. And this strain penetration depth gives us a stiffness, rotational stiffness to that spring. So if you use this equation, from moment curvature, you can get these two numbers. This one is very straightforward. This is an equation, so you can get this rotation just straight out from an equation, and that will give you the wall. Now we also wrote this out generally in the code or in the proposal, so that you can actually use this for any load level or any deformation level. So if you wanted to look at a service load level, all you have to do is go to your moment curvature diagram and get the moment and the curvature at that level, and that'll give you a stiffer response because you haven't reached all the flexural cracking from moment curvature. So that works also for service level checks. But I caution everybody in terms of loading history. You can only use the stiffer, the higher stiffness for service levels if your structure did not reach a near yield state. If your structure in its history reached a near yield state, then it has softened already. You'll never recover that higher stiffness. And so if you're looking at service level stiffness, if you know that your building has never cracked before, then you want to have the higher stiffness. If you know it's cracked before, you want to follow that. One way to do this is to actually bracket your solution, to go low and high depending on which way. One will give you higher forces, one will give you higher deformations, because you do not know what the history is and where the stiffness actually is of your building. So that's the proposal here. We also simplified it a little bit for those of you that don't want to do moment curvature. If you have one wall, that's one thing. If you have 20 walls, it adds up a lot of computation. We pulled up something from Priestley's work. It's constant curvature approach. What Priestley found is that at low axial loads and low reinforcement ratios, which is a lot of the older walls you see around, the curvature at yield is relatively constant. And the equation for that curvature at yield or at nominal strength is given by this equation. So yield strength of the bars, length of the wall, modulus of steel. So this is a very simple equation. Gives you the curvature, and you get your moment strength straight out from ACI 318 methods, and divide that by your curvature, and that gives you your EI effective. The rotational spring, you'll use the same equation as before, but simplify this. So here there is no need for any moment curvature analysis. It's very quick, it's very easy, but only works for planar walls, relatively low axial load, and relatively low reinforcement ratios, which I believe is a big portion of the older concrete walls that we're worried about. And so how does all this fare? Here's how it fares at the first story and the second story in the wall direction of the building. This is the E-defense results. Depending which way, whether you use the spring or lump the EI effective together, or do the constant curvature down here. So these are all the variations we're proposing for ASCE 41. They all do reasonably well. I mean, they're fairly close to the point where we're looking for. At the first story and at the second story, we're spot on where we want to be. And you go up the stories, it also looks the same. So this proposal is now being balloted. I hope it will pass. It does make a big difference. The stiffness of the wall will change. Now, just to note here, these walls had very low axial loads on them. That's why the stiffness is very low. You start getting up to that 0.5 EI gross if you have very high reinforcement ratios or very high axial loads. So this method, because it is just doing moment curvature, will account for all these things. If you have high axial load, high reinforcement ratio, will push you up closer to that 0.5 EI gross, or will push you down here. This is about a 0.15 EI gross. If you're question there?
Yeah, on the test data that you're trying to match or trying to envelope, I guess, particularly on the left, it seems like there's almost two sets of data. One
the data or the lines?
Well, the lines, but I mean, you've drawn a sloping line on top that's 2.5, goes down, and then there's a whole pile of stuff down lower. What's the difference between those two sets?
Well, all right, there we are. So these lines are the estimates from the methods.
Not those, the data below.
Oh, the data. So this data is just, so these are the secant stiffnesses at every excursion.
No, I mean, there's one that's 2.5. And then there's a whole bunch of
This one here. So this is the first cycle. So when you take the structure and it's shaking, it's going back and forth. You're getting all these peaks of deformation. So when we first start shaking it at the Kobe 25% motion, it goes up to about maybe 0.1% drift, its first cycle. We get that stiffness there. This point represents that stiffness at that first excursion. Then it cycles back, it gets higher, 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 gets all the way up to here past yield. And then once you start getting these, at the end of the ground motion, you get these smaller cycles, you get these deformation, okay? All right, so, and as a reminder, this is where ASCE 41 is currently, so really off. Now, in this code cycle, we're only going to touch this, but I envision taking this forward to frames also, and looking at a similar thing for frames to come into alignment with fiber section analyses. Ongoing work, this is almost complete. When these slides were printed, this was still ongoing. We've almost completed this part. We're verifying this procedure with a database of wall tests, and it actually verifies really well with it. Validated looking at the UC San Diego shaking able test, and it's looking really good with this test also. And we also are looking at what are the effects of changing the stiffness of your building from 0.5 EI gross to 0.15 EI gross, and your linear analysis procedures especially. And what we found is it doesn't make a big difference on the force, but it does make a very big difference on the deformation and your analysis. So this is something that we looked at, and this is now in the ballot. And I'd like to thank Siamak Sattar for doing the database work, and Garrett Hagen at Degenkolb for looking at some sample structures for this. And so we're confident that this works, or is the way forward. It matches up with a lot of data, and it will have a significant impact on the analysis in ASCE 41. So now on to the next topic, which is column modeling parameters and acceptance criteria. For those of you that are not familiar with these, just a quick overview of what they are. So the modeling parameters are given for columns as limiting plastic rotations. They're used to build analytical models for structures. So the modeling parameters are used to define the backbone curve, and the acceptance criteria are there to determine what is a minimum acceptable or maximum acceptable deformation for a given performance objective. Let me move here. I think I can explain it a little better. So this is the generic backbone curve in ASCE 41. modeling parameters A and B here give you the plastic rotation to initiation of lateral strength loss, and B is the initiation of axial collapse. And then you have the acceptance criteria. So for collapse prevention, I'm not sure why this keeps happening. So collapse prevention is here. Life safety is 75% currently set of the B term, and immediate occupancy is way down here. So this is the general framework that we're working with at this point. What are the issues we're trying to resolve with this framework? Well, currently the modeling parameters were selected conservatively. So if you take a parameter A with a distribution this way and a parameter B with a distribution this way, if you take the best estimate, which is take A at the mean value and B here at the mean value, you get this black curve. If, however, you choose some conservative number for A, some conservative number for B, what you're doing is you're getting a conservative analytical backbone curve. And what that does is if you have different levels of conservatism, which we have now in ASCE 41, you have, so let's say the shear wall is, somewhat conservative, the columns are very conservative, the joints are somewhere in between, beams are very, very conservative. Now you're building your modeling parameters with these offset curves, and you're not really sure what you're getting out of it. You're not sure what the mechanism is coming out to be. You're not sure what level of conservatism. If you penalize one element substantially, it'll fail first, when that may not be the case. And so the end result is your structural behavior is altered in the analysis. So that's the modeling parameters. And so the proposal here is to actually move all the modeling parameters in the document to the mean values, so that you at least get a best estimate of your analysis, and put all your conservatism in the acceptance criteria, not in the actual modeling parameters themselves. Now, talk a little bit about the acceptance criteria. Currently, they are selected as a fraction of modeling parameters, so they're either 1 times the B value or 75% of the B value, and that does not give you consistent probabilities of failure. If you look at a member with a parameter A1 and a large coefficient variation, you look at another member with A2 with a smaller coefficient variation, but A2 selected more conservatively. So one is selected at the mean value, one is selected a little bit conservatively. They have different coefficient of variations. And now what you do is you define your acceptance criteria as 75% of that modeling parameter. Take 75% of A1, you take 75% of A2, and what you end up having is here, the area under this curve and the area under this curve are very different. Your probabilities of failure are very different currently. And so we're trying to clean this up a little bit to define the modeling parameter at the mean, and rather than selecting the acceptance criteria as a percentage of the modeling parameter, we're trying to select them as a percentile of those parameters. So we get the same probability of exceedance for each of the acceptance criteria for all the elements across the document. So let's talk a bit about the scope of changes. So we're reevaluating 4 columns specifically at this point, the modeling parameters to get a median estimate. We're using an expanded database of 500 column tests. This is on the NICE hub. If you're interested in looking at the data, it's there. We're treating circular columns, which were not treated before, and I'll show that they're actually performing quite a bit better than rectangular columns. And we will be adjusting the acceptance criteria based on the new modeling parameters. We'll put the conservatism only in the acceptance criteria, and we will select them to give us a consistent probability of exceedance for all the members. Now, in this iteration, we're going to only do columns, but this should be the future for the next iteration of the document. So this is what the database looks like. If you're interested, you're looking for data, something to match, it is on the NICE hub. The distribution of the data in the column database, you have axial load ratio, so you have a good spread all the way up to 0.6, 7, or 8 times the gross capacity. The spacing of the hoops or the ties, S over D, so most of the data below D over 2, but some of it higher over here. The transverse reinforcement ratios, we have a wide range. And this is the important parameter here. This is the Vy over V naught or the Vp over V naught that you're used to in ASCE 41. If the flexural strength is much higher than the shear strength, Then you expect a shear failure. This is a Vy over V naught bigger than 1. So this is shear failures. Somewhere in between, you can have some flexural hinging, then shear failure, and down here you have the flexural failures. So we had a very wide range of these parameters in the database. So we looked at the most influential parameters. We plotted versus many things: axial load ratio, shear stress, and what came out to be the most influentials were the axial load ratio. So this is for parameter A, the initiation of lateral strength loss, axial load ratio, transverse reinforcement ratio, and that Vy over V naught term. And this is not very different from what you currently have in ASCE 41, so it's not surprising these came out on top. I want to draw your attention here to the Vy over V naught term. Anything above 1 should signify a shear failure, and currently what ASCE 41 does is at 1.01, this is a shear failure. This is categorized as a condition 3 I's, I believe, I, and you have your A parameter goes to 0 immediately. But what we've seen is that the V naught term, that shear strength equation, has its own scatter. So it's not necessary if you have a Vy over V naught of 1.1 that you necessarily have a shear failure. You have a higher likelihood of having a shear failure than at 0.9, but it's not necessary. So what we're looking at here is the rotation. Actually, there's still some life here, 2-3% rotations, and finally dies off at about 1.3 to 1.4. So we tried to bring this in to the provisions. There are also some changes in how you estimate that Vy over V naught. This is the equation, this is shear strength equation that Professor Maley has presented this morning. It is by Sezin and Maley. This is currently in ASCE 41. The big changes here is that instead of VP, we used Vy with expected material properties. So it's not the VP that uses 1.25 Fy, but rather it is the V at yield, so the yield moment with expected material properties. The reason we did this is that few columns, especially the non-ductile ones, will get to significant hardening. We're getting up to that 25% hardening. So we pegged it more towards the yield strength as opposed to the plastic strength of the section. And the second big change is we're introducing this phi factor to account for the spacing of your ties. If your spacing are tied D or more, a shear crack will just cross straight through, and the transverse reinforcement is not doing anything. So this term goes to 0. You're below 0.75, the transverse reinforcement works, and in between you interpolate. So what this does, it eliminates any strength component of your ties if the spacing is very large. But other than that, that equation is about the same as you had it before. And the other thing we looked at was the boundaries of the properties. So if you look at the table in ASCE 41 and you're looking at the transverse reinforcement ratio, you're interpolating between 0.002 and 0.006, which is a very restricted space, and your axial load is 0.1, 0.6. If you look at the data, however, the transverse reinforcement for circular columns and rectangular columns, it goes much beyond that 0.06, which is over here. And currently you're interpolating over this green area between 0.1 and 0.6 axial load, 0.02 and 0.06, where the data encompasses all this. So now we're actually expanding that scope, looking at what happens with more reinforcement ratio and bigger range of axial loads also. And the end result looks something like this. So these are equations, no longer tabular format. You have the axial load, the transverse reinforcement ratio, and that Vy over V naught term. More axial load is a negative sign, reduces that parameter. Adding transverse reinforcement increases that parameter, and this term is negatively correlated. The closer you are to shear failure, the higher that number is, the smaller A is. Now what we've observed here by taking the circular columns and rectangular columns separately is that this equation here gives you about 30% larger drifts than the rectangular columns. So that's a big change. So you will get a 30% bump if you have a circular column with spirals or hoops in it. So that's, now we're treating these separately. Analysis of fit. For rectangular columns, not too much of a change, other than moving from a conservative probability of exceedance here. It was set to about 35% for the modeling parameter. Now it's set about 50%, so we're achieving a mean or median estimate. And for the circular columns, since they're treated very conservatively, down here you have a 25% or so exceedance rate. We went back up to 50% and we improved the fit. So this is the big changes here for the modeling parameter A. For the modeling parameter B, this is at axial collapse. We do not have a lot of data. So we have some data. Professor Mealy showed some this morning, but we don't have enough to do such a regression analysis and look at the fit through regression models. So we opted to go for the Elwood and Mealy axial failure model, a simplified version of it. It seemed to work really well for the data, and this is how it fits here. So this is, and Professor Mealy showed a similar plot this morning. So this is current B value or drift at axial failure that ASCE 41 shows versus the actual measured is quite conservative at this point. And so using the proposed equation, now we have a much better fit, a nice mean value or median value for the modeling parameter that we're looking for, with the exception of a couple of points here that were cycled to 6 drifts per loading protocol or bidirectional at 3 loading cycles per direction. These were deemed to be very severe loading cycles, so we did not take them into account to reduce them. Most earthquakes will not impart this type of deformations on columns. So the model seems to fit really well with the data that were tested to collapse. If we take it to the big data set and we look at the fit, on this side is a conservative estimate, this is unconservative, this is the models B, and this is the experimental values of B. The black squares are the ones of tests that fail, that actually were pushed to collapse, so there's not a lot in our data set, but we can see that the model actually comes up, splits the data roughly in the middle, so it's a median value. And for the circular data set, we only had, I believe, 9 circular columns that were pushed to collapse, so really we did not have much to go on here. But what we find that it's still the B that we did for rectangular columns is conservative for them. So we bumped it up 30%. I bumped it up 30%, and this plot is with that extra 30%. So the B term in the circular columns is also 30% larger than the B term for rectangular columns, and it still comes out a little bit conservative given those few data sets. I was personally not comfortable pushing it any further given that I only have 9 tests. But it comes out conservative, but really not too far from the numbers. So we're happy with this. So this is what is in store for modeling parameters and acceptance criteria for the columns. We also look at splice deficiencies. I need to move it along here. So the supplement one changed things a little bit, but with very, very limited data. We brought in a data set of 39 column tests, some with very short splices down here, some with conforming splice length. Looking at what currently the ASCE 41 procedures are, if you have a splice length that is greater than the development length given in ASCE 318, you say there's no splice failure. Otherwise, if it is shorter than this number, then you'll compute this FS, and that is the stress capacity at splice failure. And the modeling parameters that ensue if you have a splice failure are extremely conservative. Just basically, the A value goes down to 0. So this is what is currently in the code. So we took that and looked at it with the data set that we have, and we split the data into 3 categories. So category 1 is splice failure before flexural yielding. Category 2 is splice failure after flexural yielding, and category 3 is no splice failure experimentally. And so if you look at the splice length versus the development length in ACI, a value below 1 means that the method says there should be a splice failure. Above 1, it's no splice failure. For category 1, the development length of ASCE 318 seems to be doing a good job determining most of the data to have a splice failure. And at the other extreme, those that did not have a splice failure, also the development length of ASCE 318 is doing well. But in the middle, we found a lot of unconservative things. So for these columns that yielded a flexure and then saw a splice failure, we were kind of split in the middle with the development length of ACI really not giving us a good sense of which columns are failing by splice or not. And so we bring in a recent experimental to explain this. I look at tests I conducted recently on a column. This is a high strength steel column but had no splices, just longitudinal bars with very high bond demands and shear demands. And this column failed by this bond splitting here. Effort of saving some time, I'll skip the video. What this shows, well, actually, everybody likes this small video here, but let me fast forward a little bit here. So this column is being cycled, and these are the principal strains on the surface. And what you see is it reaches its peak strength, starts yielding, but the splice, the bond is still holding. Then you start getting damage at the ends here, and once the plastic hinge region gets damaged sufficiently, now we're at about 3% drift, that is when the bond failure occurs. So it unzippers. So bond failure did not happen at peak strength or at peak demand. It only happened after significant damage occurred in the plastic hinge region. And so if we do run the numbers on this particular columns, what you find that the undamaged available development length, which is the shear span, is 42 inches. ACI 318 tells us we only need 37 inches of development. So technically this column should not have a bond failure. However, if you take out about 2/3 of the depth of the section, which is kind of the plastic hinge region that got damaged, you drop down from 42 inches to about 32 inches of available development length, and that drops down below the number, and you do actually see that that bond failure. So we're not taking into account this damaged region. And so if we go back to that data set and say, well, let's say if I take out that 2/3 of D for all those columns that yielded and then saw a splice failure, we get to here. So this does not get affected because we don't take any damage out here. These failed by splice before yielding. For these columns, however, we take out that 2/3 D, and what we get is now they're correctly categorized where we want them to be as splice failures, but only splice failures after plastic hinging occurs. And so we are proposing now to change a little bit the provisions in ASCE 41 to say, well, if splice length is greater than the development length in ACI 318, then you should look at if the splice is out of the hinge regions, you should not have a splice failure. If the splice is in the hinge region, you should then check that LD versus an adjusted length, taking out the damaged region. And if you do have a splice deficiency, then your FS should be evaluated here or here with the original, I'll use the mouse, original development length or the degraded development length here. So this is the change coming here, and we're also proposing to change, give a little bit of life after bond failure based on the amount of transverse reinforcement in the section. And this is what the tables look like now in the ballot. So the equations for A and L, B, A, B, this is the residual, and this is for the splice deficiencies. Now to acceptance criteria, and this is the last heavy slide of the presentation. As I mentioned, we're trying to get, instead of percentages, instead of saying, okay, well, acceptance criteria is 75% of A or B, we're trying to get probabilities of exceedance. And so if we consider that we can take a 10% probability of exceedance for life safety on the B term and 25% for collapse prevention, if we look at this is looking at the multiplier to achieve these probabilities of exceedance for that B term. Since we aimed for 50 percentile, so 50% probability of exceedance is 1. This is the current B. This is the mean value. 40% probability of exceedance, you multiply by 0.8. To get 25%, you multiply by 0.7. And to get the 10% probability of exceedance, you multiply by 0.5. So I determined to take the 10% for collapse for life safety, 25% for collapse prevention. And these are the 0.5 and 0.7 multipliers that are here. So now you have life safety is 0.5, the B term. Collapse prevention is that 0.7 of the B term here. So this completes the modeling parameters for columns with splices and acceptance criteria. Lower bound are expected. You may be wondering, if you viewed the document, which material properties to use. We have not resolved it fully, but we're taking an approach at least and starting to clean out the document one step at a time. For force controlled actions, we're saying that we will use lower bound material properties, which makes sense. For deformation controlled actions, we are proposing to use expected material properties. For modeling parameters, which are for nonlinear modeling parameters, usually you'll use the expected material properties there. For classifications, if you're trying to classify something, so looking at your joint, if you're trying to classify to figure out which stiffness to use or something like that, or any triggers, we are proposing to use the expected material properties, so you get the best estimate of the actual classification that you're going to be using. And here's where our hang-up is for combined actions. If you look at something like axial bending interaction, do you take it as expected or as lower bound? It's not really clear depending on your failure mode. So at this point, we're leaving it to your engineering judgment until we come up with a better proposal. It gets a little tricky when you have these interactions to go in place. So now we're cleaning up the document as best we can. We'll get some of it done this cycle, and we'll hopefully get all this cleaned up for the next cycle. Now the longer term changes, I have a couple more minutes. What are we looking at for the next cycle? Although I think the anchor testing will make it this cycle, I'm optimistic. Currently we don't have anything for post-installed anchor testing in ASCE 41. So we're introducing this. Also, big change from other testing procedures is to allow to test to a desired level. So not to failure, but test to a certain strength level and stop there. Insan Kim at Deng & Co was leading this effort. We're looking at changing the beam modeling parameters since the columns have been shifted so much from very conservative to median values now. The beams are left at very conservative, and so now beams will fail, even though they should not in your analysis. So Professor Matamoros is looking at this one. Looking at the modeling parameters of slender shear walls, we're not sure how accurate the current provisions are, so Professor Byerly at A&M is looking at that. Beam column joints, while Hassan and Laura Lowe's are looking at that. Expect major changes there. There's a lot of things coming out of the Grand Challenge and other work that are going to fit into it. And I'm hoping to bring in the frame stiffness in line with the wall stiffness. Now, something separate from all this that we may bring in later into the document, we're also looking at retrofit modeling parameters and acceptance criteria. We're starting with jacketed columns, and we're moving forward. So if you jacket a column, what are the modeling parameters and acceptance criteria for that? Professor Brenya is working on this at UMass, and depending how it progresses, it's possible for the next cycle it may get into the document itself. And finally, some methodology work. There's an ATC 114 project now that's currently looking at the entire methodology of ASCE 41. They want to expand the backbone curve, trying to find ways of introducing cyclic damage. So it's not a static backbone curve, but it shifts depending on the cycles. Looking at introducing the probabilistic framework of the acceptance criteria, something I talked about here. So this is ongoing work, but it will not make it for this cycle for sure. This is going to be for the next cycle. Hopefully we'll streamline the work. And I believe that is it for me. Thank you.